part of the reason I can join the workshop is because I'm doing a sabbatical here, and another reason is because of the name FUNCHEM. I like it. I think whoever invented that deserved an award. As atoms and chemists, we all love acronyms. There's tons of acronyms you're going to see. For those audience, particularly not familiar with, not from North America, so you may not familiar with some of the terms I'm going to talk about, those field campaign, weekend, fire XAQ, Samosa, which is a smaller campaign. But in general, my group is a joint experimental and modeling group. We use all kinds of observations from aircraft on the ground and satellite to answer those questions. What's in the smoke? What are the chemistry and the reactivities? And more importantly, how do those fire smoke affect urban photochemistry? And we use a model to test our understanding of those chemistry and emissions. So again, give some audience who are not from North America some ideas why it's pretty big deal in the US and Canada to study wildfire at this moment. This is one of the recent papers looking at essentially showing that wildfire smoke is erasing those progress we made through those Clean Air Act. So show those PM trend over the last 20 years, you see many regions starting from around 2015, 2010, so this PM trend is flattened out. And some regions, particularly in the Northwest and the Northern Rocky Mountains, you see those trends starting to picking up. And this is another recent paper looking at some things this group may not particularly pay much attention, is the greenhouse gas. And it's looking at last year's the mega fire or gig fires in Canada, and using this NASA scientists using satellite remote sensing to do inversion of CO and then to back calculate the CO2 emissions from the fire. And the conclusions is those fires from Canada last year's gig fires is equivalent to, if that's a country that's ranked the number 4 in terms of anthropogenic carbon emissions. So it is a pretty big deal. Something we are interested in is particularly on atoms and chemistry is, I think that we can put in a way to say that we don't quite understand fire's role in affecting, particularly in tropospheric ozone and its role in the climate. This is a study in my group, and we're looking at the NOx emission. The study itself is trying to improve the anthropogenic NOx emissions. So we tried our best to tune the model for the NOx emissions, and we found that anthropogenic emission, there's a lot of uncertainty, but once we correct that, reduce the NOx emission, you see the model is not really doing well compared to ozone sound, and fire could play an important role there. There's another study specifically looking at fire-related ozone using ATOM aircraft campaign. Essentially, that's the aircraft flying around the globe, going up and down, and trying not to, and the goal for that is try to provide unbiased sampling. So they are not trying to presume any urban plume or fire plume, but just going up and down. And so you see that this is a figure that for ozone attributed to biomass burning, and ozone on x-axis is ozone attributed to urban emissions. Green symbols representing this observation, and the other color is representing the model, essentially suggesting the observation from this ATOM aircraft measurement suggesting that lots of those ozone in a remote atmosphere actually are due to biomass burning. But the model on the other side, contrary to suggesting model, is essentially attributing a lot of ozone attributed to these urban emissions. So that's a significant knowledge gaps. You heard many talks already talking about these potential knowledge gaps, about the fire emissions, the timing, size, and my group particularly interested in the composition of those emissions. And we made a lot of progress in terms of understanding the plume scale, smoke chemistry. And there are also tons of research groups working on plume injection heights. And also, I think a question got asked in this afternoon about how to represent this subgrid process in the global model. There's a lot of interesting questions. We don't have the answers yet, but we made some progress. So my group, particularly using a tool called photon transfer time of flight mass spectrometry, to measure a whole suite of those organic carbon in the atmosphere, and we compare to the model. So this is the figure. Let me orient it for some folks who are not familiar with this kind of analysis. On x-axis showing the mass per charge ratio, and the y-axis essentially is the measured concentration, and each bar could be representing just one or multiple species we've seen from this kind of measurement, right? And this also different colors for another different study, so it doesn't matter that much. But it's just give you the representation showing we can actually measure tons of a lot more species than our current model representing. So this current model representing those arrows, downside arrows, that's typical model only representing 10 to 20, 30 at most VOCs. And you see they're missing a lot. So the question we're trying to answer is, does those model really missing a significant amount of those reactivities from those VOCs in different environment, in Arctic, in fire smoke, in urban atmosphere, and what are those really implications for our capability to simulate ozone and particulate matters? So let me introduce the WeCan, and this data set has been widely used in US and by US researchers, and hopefully we can just people can other researching in other parts of the world would become interesting in this data set. So this 2018, we used the C-130 aircraft to sample 20 large fires. 20 does not sound a lot, but essentially it's double the number of those airborne samples. And 2019, NASA and NOAA carried out a FireXAQ aircraft campaign, essentially that the sample size was doubled again, right? So we have tons of those samples. This map showing those aircraft tracks from the WeCan, and we reported 160 different VOCs compiled from 4 different types of mass spec based equipment. So that number essentially is doubling the number of VOC ever reported. And there's many of those VOC, that was the first time getting reported from field observations, but previous report in the laboratory experiment. You'll see one of the slides show why that matters. And again, FireXAQ essentially is providing additional data. And this is, so we have really comprehensive data set in terms of VOC and many other gas and particulate matters. So let me give you a brief, very simplified view about VOC emissions, the difference between biomass burning and biogenic and aspirated emissions. So we're not here talking about biogenic emissions, but in general, those isoprene and terpene dominated, right? And there's some other smaller oxygenated VOCs. And it's getting a lot of attention for those the often used aspirated emissions or VCPs. So many of them also oxygenated. So we're not talking about that either here. It's a major difference of those fires, open fire, and those controlled fires from vehicle, from manufacturing power plants. Essentially, you can think about the different major features. First of all, the fuel composition is different. Fossil fuel, typically, the majority of the composition is hydrocarbons, right? Carbon and hydrogens. But fires, burning biomass burning, you get tons of oxygens, not half, but 40%-ish of those composition, those element composition are coming from oxygens. So that makes a lot of difference from the emissions. And you also have tons of moisture in the biomass. So we know fuel moisture also make a lot of difference for the emission composition. And the combustion condition is quite different. One is controlled and it's designed to burn completely, right? There's nearly complete internal combustion engines. And the other one is uncontrolled, incomplete combustions. So that's like we learned from the high school or middle school chemistry class. If you mixture your fuel and air or oxygen in a perfect ratio, you can have complete combustions. But if not burned completely, you can have CO and some other impurity pollutant generated. And the temperature also matters a lot. One at above 2,000 degrees Celsius, another is 300 to 1,000 Celsius. And that temperature essentially contributed a lot, as currently we understanding, contribute to NOx emissions from different burning, right? If you burn at a very high temperature, you're going to generate this thermal NOx. Essentially, the temperature is high enough to break NOx N2 from the air. But at a low temperature, those nitrogen need to come from your fuel, right? Coming from those biomass. So in general, NOx emission is relatively low compared to anthropogenic sources. So with those ideas in mind, if you look at what we learned from weekend fire XAQ, we see this fire, as we anticipated, as we hypothesized, is emitted tons of those VOCs. This pie shows the top 10 VOC species emitted from the fire emissions. And you have a lot of very familiar names: organic acid, formaldehyde, and acetaldehyde, those small OVOCs. Essentially, those top 10 account for half of those VOC mass, and oxygenated VOC as a lot, as a whole. And you can have those, if you look at the health impact, you have tons of those hazardous air pollutant can rank those top 10. But I'd like to point your attention to these cumulative lines. Essentially, top 10 is right here, account for half of the emissions, right? And the rest of the half mass actually needed to be accounted for, coming from accounts of those 130, nearly 130 different species. And all of them are emitted at a relatively small amount, but adding them up matters a lot. And so this figure essentially, I think, sometimes gives us a little hope to thinking about the predictivity capability. But I think we have some predictive power for those VOC variabilities. And this is showing those emission factor plotted against the modified combustion efficiency. And as it's been introduced in the morning by various talks, you have the Fleming and Smoldering process, and MC essentially can explain a lot of the VOC emission variabilities. This is not new, and 20, 30 years ago, biomass burning studies since 3 decades ago report this a lot. But this one will provide those statistical numbers for those 160 different VOCs, reporting for all those relationships. So allowing us to use this kind of relationship to back calculate the emission factor, use MC. Particularly considering nowadays the MC is the parameters prioritized by the satellite remote sensing community to be observed from space, right? This work was done by my student Wade Perma, and one of the I will show this difference of the in this figure to show the difference between laboratory and field data. And we tried hard to understand the difference of those two. I don't think we have enough knowledge. We have some leads, but we don't quite understand yet. So this plot those total observed VOC emissions plot against the MCE, right? The previous slide showing those individual species, here showing the total VOC. And the laboratory study all show in these orange lines. You see those in the field data, we essentially show those slope is much lower, is a factor of two lower than laboratory data. We think the ambient measurement temperature could matter because the aircraft measurement was done at a high altitude. There may be some evaporations and some other condensation process, but we're not sure. But here essentially is really highlighting the importance of those field data, field observation of those real fires. So my other students trying to use this data set to test the model. We tried really hard to test the model for different, for example, for the vertical injection height schemes, and try different emission inventories. And the figure on the left essentially summarizes the results. And the vertical profiles for observed VOC, one for formaldehyde, one for benzene. The y-axis is a pressure level, and x-axis is a mixing ratio. So, and different color show that the model driven with different emission inventories, the commonly used emission inventories, right? We found that for those oxygenated VOC, like formaldehyde, acetaldehyde or those oxygen VOC, different model essentially different emission inventory doesn't matter that lot. And even with tripling the biomass burning emissions, that does not change a lot for the model results. But for the primary species like benzene itself, of course, the default emission inventory is underestimated fire source. But when we're tripling the biomass burning emissions, this is the dashed gray line. Essentially, they can match the observation better. Okay. We also try to look at those emission factor, whether they can explain this discrepancy. We found the emission factor for benzene, for formaldehyde, and all those VOC implementing in the model they actually can agree well with the observation. So what matters here is the biomass consumed or effective biomass consumption. That number matters a lot to close the gap of factors 3 to 7. So there's another issue in the model. As I mentioned, the model only simulating 10, 20 VOCs, but we measure 160s, right? And this figure essentially showing the model. If you count all of these simulated VOCs, look at the emission ratio to relative CO, you get a 75 ppb per ppm CO. But observations suggesting that number is twice bigger, right? So suggesting those missing VOC in the model, that's a significant number. And those VOCs are those furane containing species, terpenes from fires and butanediol, et cetera, et cetera. So if we're adding all those missing VOC together to correct the model, this will be the VOC emission budget we think is for that year, 2018 summer. The biogenic still is the largest source in the Western US because those conifer trees emitting those terpenes. And anthropogenic is roughly just quarter of the biogenic source. But the biomass burning, essentially, that right now can account for half of the biogenic source. So it's ranked number 2. Previously, this number in the default model, whatever emission inventory you're using, that is only give you like 200 to 300 gigagram carbons. And this, in general, is still a lot of work need to be done to look at fire emissions for particulate matter, for CO, and also the greenhouse gas. So because of those survey, those aircraft data, this allowing us to look at chemistry in great details. And one for the metric we use is called OH reactivities. Essentially, that's the concentration weighted by the rate constant, reaction rate constant against OH. So OH reactivity in the wildfire is widespread. It's spread across many different species, and then in urban or in forest. So here's this is the figure showing the pie chart and proportion of different function groups to the total VOC OH reactivities. And again, is very important in emissions, and they became less important in aged smoke. But furane is still present in both fresh smoke and aged smoke because some of those relatively longer-lived oxidation products. And some other OVOC became more important in aged smoke as well. But when we look at look at urban, how they interact with urban, this is just the sample during weekend based on one middle-sized city in Boise, Idaho, in the western US. And the biomass burning emissions, we found those when the city is impacted by smoke, the OH reactivity is increased by nearly 50% because of those VOC and CO present contribute to the urban atmosphere. But the NOx is not enhanced when smoking was impacted during the weekend. And this essentially use some metric we can look at those the ozone photochemistry, essentially those promote ozone production to more optimal conditions. So NOx matters a lot here. we know the impact of fire smoke in urban photochemistry would depends on how old the smoke is. In the very fresh smoke, when you near close the fires, you're going to have tons of the VOC ultra-activity added. But it also enhances NOx. But in aged smoke, essentially they have less VOC added, but also has little or no NOx because the NOx has been rapidly converted to other reactive nitrogens. We saw the other example we showed is in Somoza study in Salt Lake City. We found out this again used the metric NOx reactivity versus VOC reactivities. So if the ratio is below this threshold is pretty low, is 0.02, that can be considered as NOx limited. So as you can see from this figure, for that summertime, in Salt Lake City, essentially the whole city, the city is quite VOC limited region. And this orange dot highlight those days when the city was impacted by wildfire smoke. That it tells us from this data set, looks at the fire smoke essentially did not affect the photochemistries. And compared to previous ones, in Boise, Idaho, during weekend, the fire smoke enhanced ozone photochemistry there, right? What I think what's happening here is, well, this is showing the diurnal profile of NOx and the total observed VOCs, colored by no smoke days and smoke days in red. And we know the fire smoke can bring a lot of VOC in town, into urban atmosphere. So essentially, you see those VOC concentration is enhanced, right? But in Salt Lake City during that time, found that on the smoke days, the NOx also was enhanced. So what it means in that case is that ratio did not change that a lot due to smoke. So to summarize that, thinking about smoke can bring VOC for sure. We have a lot of observations suggesting that, but it's the impact, I mean, the effect of NOx is unknown. In some places, in some times, the NOx can be enhanced during smoke, but sometimes not. Maybe it depends on the proximity of the fire and the city, and sometimes it also depends on the PAN somal disruptions. I have a few more slides, and then we can wrap up. We also look at those very detailed plume chemistry, and this on the right side showing aircraft track and following track those one particular fires is called Taylor Creek fires during weekend, right? And essentially that's called it's called pseudo Lagrange sampling, trying to sample the air mass again and again as it's moving downwind. We use different VOC ratios to back calculate the OH concentration in these plume. And these are the complicated figures showing that estimated OH concentration plot against the photochemical age and colored by different fires. But let me just draw your attention to one fire, these Taylor Creek fires here. You see that one of the things, the OH concentration is elevated a lot. This give you a reference of ambient OH concentration. Is essentially 10 times higher than the ambient OH concentration because it's initial whole node concentration emitted by fires. And it depleted really fast after 1 hour, 2 hours. And because of the tons of other VOCs consume OH really fast. So to account for these rapid change of OH concentration in the plume, the model, we found we need the model to be initialized by whole node for sure to get OH source correct, but it also requires the model to be initialized by 100 different VOCs to account for these evolutions. So the model line, those are two dotted lines and dashed lines showed two different models, and that showed that one of the model is the typical chemical transport model. This is geochem's chemical mechanism, only have 20 or 30 different VOCs. You see those, if you not have 100 VOCs in a model, essentially your OH concentration will be overestimated by nearly 50%. We're doing the similar things for the plume chemistry for ozone, for PAN. This on the left side showing the ozone enhancement relative to CO, plotted against the physical age. Again, the fires, fresh smoke generate ozone rapidly, but each fires can have total different ozone chemistries. But when we plot them against the chemical age, that essentially tells the chemical age can help explain majority of those variabilities in ozone productions in the smoke. So over the past few years, you see, notice lots of paper coming out of the weekend of FireXAQ look at this plume chemistry in great details. I think we understand made a lot of progress over the last few years, but right now we add this stage to really help transfer those findings at a plume scale, plume levels to regional and global model. And one of the things my group is doing that essentially is implementing these new previous under-characterized, unmeasured species, the furans in global models. We add those furan. This furan is the 4-carbon rings with oxygens, and they have different function groups. They can have different derivatives, but they all can react with OH, and depends on if the ring can be break or not. This have different oxidation product, and they can generate maleic anhydride, which is one of the hazardous air pollutant, and that all those, and also oxygen, smaller oxygen VOCs, and it can make CO, PAN, ozone, SOA, etc. So this is the first time we're trying to implement this global model. We found this initial look at this looks very promising. Look at the annual concentration of OH being changed, and ozone being enhanced by 15–16% on annual average. And one particular things for glycol, for those folks interested in organic aerosol, is the glycol's burden in the model being increased by 50%. That is important precursors for SOA globally. So moving forward, and have 2 more slides, is we are starting thinking about the solutions. And this working with my colleague Bob Yoxon at the University of Montana, and we're starting thinking about the science to expand the spring and fall prescribed burning, as that's really wonderful ways to mitigate the risk of wildfires. This is showing figure. Bob's figure show the fuel burned for wildfire and prescribed burning. Currently, prescribed burning is only fraction, the burn area is only fraction of the wildfires. Right, but in the future, the U.S. The Congress is investing a lot to carry out more prescribed burning in the U.S. And we know that emission factors for wildfire and prescribed burning are different. And although there's limited observations, so we're trying to use developing a mobile lab to carry out this emission measurement near those prescribed burning. And this is a figure showing my group during the site visit of the prescribed burning in the spring. And we see this beautiful flaming on the background. So we took this photo and as a group photo. And then 30 minutes later, this photo was taken just maybe 20 meters away from this photo. So 30 minutes later, you see this, it's getting very smoky. So the fire system changed a lot dynamically, and we really need some mobile capability to capture those life cycle and spatial distribution of those fires. Hopefully we can use this measurement to help us in understanding not just prescribed burning, but also wildfires dynamics. With that, thank you very much.
Thank you for that very interesting talk. Do you have any questions? A quick question, maybe? Yeah, Claire or Hugh? Go pass off.
It's a long day.
Yeah.
Great talk, absolutely fantastic analysis. It's really good to see. I was wondering about the lab-based versus field factor of 2 in your emissions versus observations. And I wondered whether you could speculate on what the underlying causes might be.
Yeah, we can. So first of all, one of the hypotheses, okay, people in the room understand this emission inventory. I think it's been brought up a few times in the morning. They typically use those compiled emission factors, right? And they're coming from the lab. Many are coming from the lab. But field observation, particularly from either on the ground or from the aircraft, those field observation typically is considered slightly aged. Well, in the lab, you can measure maybe second old from the fires, right? You can get really close. And in the aircraft, 10 minutes is that the closest you could get for safety reasons and logistic reasons. And many of the aircraft measurement for the emission measurement, it could be even longer, 30 minutes or maybe 40 an hour. And obviously, we try our best to avoid those aged smoke to analyze the emissions. But there are some of those some aging. You can see some of the age, some aging process in our emission data. So we did some detailed analysis, look at those speciated emissions. Indeed, we found out those very reactive species, the emission ratio tend to be lower in the field observation than in the lab, suggesting there's some aging, right? But I don't think that's the only reason. And there are also some hypotheses particularly for aircraft measurement, because you need to be, the fire need to be hot, burning hot, to be elevated to a certain altitude to be measured by aircraft safely, right? So in that regards, those aircraft measurements tend to biased towards flaming emission than smoldering. So, well, in the laboratory measurement, you measure the lifetime of the one individual fires. So that difference of those sample could, the nature of those sample could explain part of it. I think we wrote a few in the paper, but there's one more thing I think, as I mentioned, is the measurement temperature. The laboratory measurement typically will carry out at those room temperature, right? But aircraft is like 5 kilometers above ground. That's much lower. And how the impact, those mass spectrometry measurement, those ambient temperature, how the impact that is currently, I don't think we have good understanding about that. But there's a few speculations.
Thank you. I mean, that's kind of where my brain had gone with all of that. So you described that far more eloquently than my befuddled kind of ideas in the middle of all of that. I think that's really useful. From an aging point of view, I wondered if you could look at some of the highly oxidized material that probably wouldn't age much further and see a closer ratio. So in terms of sort of reactivity, you see different ratios for different reactivities, and that might be able to diagnose the first point you made. My feeling is that there's also this question of not only flaming versus smoldering, but the fact that when you're in an aircraft, you see a blend of the two because they're mixing together on spatial scales that are less than you can see, and that plays a role as well. But my question then is, where do you go from there? If you're going to compare emission factors or emission ratios with a model, where do you put your money?
I'd put my money on the field observations.
Good man.
that's why we highlight those really need the field of more field observations to look at them, right? We're trying to be really careful about how to carry out those field observations. But that's the laboratory experiment. They are important. Essentially, they are the reason why we're here, to have those global emission inventories. But as we have more field observations, particularly over the last 5 years, and I think it's at the point we can start to lean towards those field observation when we compile those emission inventories, in particular on emission factors. There's also, for other reasons, I think some ask those subgrid process, essentially for global model, even at 10 kilometers, 25 kilometers, they won't be able to resolve individual fires. So there's a study to suggest there's at data resolution, the slightly aged emission actually may provide better or more realistic results.
Yeah, quick question, Claire.
So I'd be more interested in following on this one, because, you know, in terms of arguing that the field measurement makes more sense, even if you can understand what's happening at a second by second level at the flame front, what is it, you know, what do you mean by it being emitted into the atmosphere? As like actually, we couldn't utilize the measurements of what's happening in terms of fresh smoke, as in aged by a second, into any model that we could use for air quality anyway. So anyway, I'm wittering now. It's the time of the day.
I'm sorry, I did not get the question, but it's, one way I'd like to comment on is I should not say, we should not say ignore laboratory data, obviously, but laboratory data I think would be very useful to bridge the gaps in the field data.
Yeah, I guess in a laboratory you can test different variables in a way that you would need a lot of aircraft funding to be able to get enough data to do that in the field.
Yeah, that makes total sense.